haven't paid yet though.
Okay, should be all right. Your first written paper is this coming week, right? Next week.
Yeah.
Okay, cool.
21st.
All right. Let's just start with any questions you have.
No.
Okay. We've been doing quite a bit of organic. Done quite well on the maths part as well, the physical bit. Okay. Let's do a bit of inorganic. Okay. Let's talk about solubility of salts. Let's start with an easy one. Actually, let's start with thermal stability. I think that works all right. Can you explain to me the thermal stability of the group 2 carbonates?
Yeah, it increases on the group because the size of the cations increases on the group. So if the size increases, the charge density of the cation increases, which distorts the anion less, which means that the bond is harder to break.
Okay.
CO.
Can you tell me the solubility of the group 2 carbonates?
Group 2 carbonates. Carbonates are quite large, so when thinking about solubility, to look at the enthalpy change of hydration and the lattice energy. Since carbonate is quite large, then
how large is carbonate?
Larger than hydroxides, but smaller than sulfate.
How big is an atom?
In nanometers.
In whatever dimension you want to say. How big is an atom?
How big is the small, but
yeah, how big is an atom?
Very small, but
and you can't see with your eye, you can't see with a microscope. How big is an atom? That's the question.
How small is an atom?
Yeah.
In nanometers. How much?
Doesn't matter. Whatever scale you give me should be alright. But as long as you give me a sense of how small it is. Do you know?
1 over 10,000 times smaller than a strand of hair.
Then how big is a strand of hair? So you said 10,000.
About a millimeter. Right?
So you're saying an atom is about 1 millimeter?
No, 10,000 times smaller than that. About.
Which is
100 to 20 to 100, like that, 200 nanometers.
Say 20 to 100 nanometer. Is that what you're saying?
Yeah.
20 to 100 nanometer. No, that's still way too big. They'll be under nanotechnology already. So if you can have like 20 to 100 nanometer, there'll be nanotechnology. And on an atomic scale, it's even smaller than the nano. The average size of an atom is about 10 nanometer. Sorry, 10 nanometer. It's about 10 nanometer. So, sorry, not 10 nanometer, 10 nanometer. About 0.1 nanometer. There's 10 to the power minus 10. is a very easy scale, 10 to the power minus 10. Okay, or
Yeah.
some people would call it 100 picometer. I think that's all right. Yeah.
Yeah.
So 10 to the minus 10 will be 100 times 10 to the minus 12. There will be 100 picometer. So we're talking about like 100 plus picoscale. But anyway, when you say big, then the most obvious question is how big is big, right? Okay. And then I don't know. What is the average carbon-carbon single bond length?
About 140 nanometers. Wait.
Again, you're going to the nanometer thing. When we just talk about the average size of an atom is like 100 picometer. When you have two average atoms bonded together, you're somewhere around, I don't know, 200 picometer, 300 picometer, I guess. You get the idea? Of course, when you get single bond, double bond, stronger interaction, weaker interactions, they can differ a little bit, but you shouldn't be looking at like 100 nanometer. That would be quite long for a chemical bond, all right? Okay, so the idea of like how small is small, how big is big, that is quite important to know because it's simple things. Right, you can easily ask someone, and then you find out that oh, actually they don't actually know the most simple thing of all. Okay, all right. Uh, where were we? Solubility of group 2 carbonates. Yeah. Do you want to write me an equation for the solubility of group 2 carbonate? Like, if I want to dissolve up a group 2 carbonate, can you write me a general equation to show what is actually happening when I dissolve them up?
Okay. MCO3 becomes M2 plus CO3 2 minus.
Okay. We are talking about dissolving up something, right? So dissolving in water. So do you want to level for me the stat symbol so that we are clear because in energetics, these things are very important. Okay, cool. You were explaining just now, you were talking about something about lattice energy, right? Do you mind just drawing me on the diagram how you're gonna relate them to lattice energy? If you can complete a hash cycle, how are you gonna relate that to lattice energy? Do you understand the question?
Yeah.
Because you were explaining about lattice energy just now, so I thought like given this question that you just you can link them out, you can hook them up with a lattice energy representation as well. We did the same diagram. Can you?
Yeah. Lattice
Okay.
energy is forming a solid lattice from its gaseous atom. The sun.
Okay.
And then
Can you complete up the cycle?
yeah. Dissolving gaseous ions in water is the enthalpy change of hydration.
Okay. Okay. When you say hydration, so you are hydrating which ions?
M2 plus gaseous and CO3 2 minus gas.
Okay, cool. Can you tell me what is the relationship between hydration enthalpy and the thing about the ions? How does hydration enthalpy changes as the ions differ?
Um, as you go down the group, the size increases. Size of the cations increase. As you go down the group, size of the cation increases. So charge density decreases, which means the attraction between the water molecules and the M2 plus ion would be less also. Which means it releases less energy. So double change of hydration less negative down the group.
Sorry, can you say the last bit again?
As you go down the group, the size of the group 2 cation increases, so the charge density decreases. So the attraction between water and M2 plus also decreases. So that means the enthalpy change of hydration becomes less negative.
Okay, becomes less negative. Oh yeah, less exothermic. Okay. Anyway, you were just talking about hydration of M2 plus. Can you draw on two separate diagrams? What do you mean by hydrating M2 plus and hydrating CO3 2 minus? What does it bring you in your head? You know, what do you imagine when they become hydrated? What are you imagining?
So the oxygen from the water molecule faces the M2 plus ion because the oxygen is delta minus and then the M is positive charge.
Okay.
So
Okay. So what do you think happens in you have drawn it as dative covalent bond? Do you think that really form dative covalent bond or
oh wait, no, it's just ion dipole attraction.
so is ion dipole bond attraction, like you said, is it stronger or weaker than a dative bond as you have drawn?
It's weaker because it's just an intermolecular force of attraction.
Okay. And you were also what you have drawn is more like a Mg2 plus surrounded by 6H2O as a complex. It's a complex. It's not a transition metal complex. It's a group 2 complex. It's a magnesium with 6H2O and 2 plus around it. All right. Okay. Let's talk about that species. Now, actually, let's go on to the how would the CO3 2 minus look like when it gets hydrated?
The hydrogens from the water molecule would surround the carbonate. So hydrogen is delta plus. So it can form dipole ion interaction.
Okay. Show me a diagram once you're done.
Okay, it's right, yeah.
Can you specifically draw out the CO3 2 minus and show me how they will interact?
CO3 2 minus. Okay.
Yeah, display the CO3 2 minus. Because what you have drawn is just an ion, which is CO3 2 minus there. You've just written it out like that. But I'm interested to see how would it look like. Yeah, okay.
For now.
So how would the water molecules interact with it when it gets hydrated, as you said?
Oh. Oxygen. The hydrogens face the O minus. So
Okay. Um, if I tell you that even the carbon-oxygen double bond is supposed to interact with the water molecule as well, can you tell me why that is? You just said like the OH2 would just go for the hydrogen of the water would just go for the O minus. Why not the C double bond O?
The C double bond, the oxygen has a delta minus. So it can form permanent dipole attraction. Yeah, permanent dipole attraction.
Yeah, what can you tell me about the individual bond length on the carbonate? So in the carbonate anion, what can you tell me about the carbon-oxygen bond length? Anything you can tell me about the carbon-oxygen bond in the carbonate anion? Anything interesting?
The carbon double bond O is shorter than the carbon single bond O.
Oh, okay. So you know that double bond is shorter because of the stronger, not really stronger pi, but because you have additional pi overlap, which means two bonds are stronger than a single bond, right? Sigma plus pi is stronger than just a sigma on its own, but obviously a pi is weaker than a sigma because it's not head-on bonding, right? Okay, but anyway, I have a crystal structure of it. I have an X-ray crystal structure with a carbonate anion, and my X-ray crystal structure show me that actually all the carbon-oxygen bond length are the same in the carbonate anion. All the carbon-oxygen bond length are the same. Why is that?
Because of resonance. The pi bonding is delocalized across all the 3 carbon oxygens. So
Okay,
the electrons
all right.
are localized.
Okay, cool. So the whole thing is a trigonal planar structure with the p orbitals all parallel to each other, so they can overlap very well with the delocalization of it. And it's the same thing in benzene as well. That's why in the crystal structure of benzene, the Cocoon structure is misrepresented because it's not alternating double and single bond. It's actually continuously being delocalized, and hence you don't get that characteristic of a double bond. You don't get that characteristic of a single. Get somewhere in between. The bond is shorter than a single bond, but longer than a double bond because it's distributed in between. Same thing in this carbonate. And that's what the actual X-ray structure will tell you. It tells you bond length are being identical, and it tells you the bond angle is 120 degree, which support the sp2 hybridization theory. Yeah. Okay. Going back to that, when you talk about the hydration of the carbonate, you kind of seem lost because you couldn't imagine overlapping these theories together. So you know about this delocalization of electrons, and therefore essentially the negative charge is not localized on just the O minus. In fact, all the oxygens, the negative charge, it gets spread around. So instead of a -1 and a -1, what you have is like a -2/3, -2/3, and -2/3. So because it's spread out, imagine -2 spread out between 3 oxygen. And essentially like all the oxygen will have a net negative charge. And that's how you can get almost equal interactions with the delta plus hydrogen on the water molecules, right? Ion dipole. Okay, so you cannot make mistakes like that. Okay, obviously they can try and correct you, but you pick it up pretty well. Okay. Um, okay, so how can you relate that? Can you now explain the solubility of group 2 carbonate down group 2 based on your hash cycle?
Enthalpy change of solubility is equal to enthalpy change of hydration minus the lattice energy. And then the more exothermic the enthalpy change of solubility value is, then the metal carbonate would be more soluble.
Okay.
Down the group, enthalpy change of hydration decreases, but lattice energy also decreases. So we need to find out which one decreases more.
Okay. How would you decide that?
Normally, we compare the size of the carbonate ion and the metal cation.
Okay. Then how will you come up with the solubility trend then?
For for hydroxides, the enthalpy change of lattice energy increases for hydroxides, the lattice.
Wait, did you just say hydroxide?
Yeah, I'm comparing it with hydroxide.
But we're talking about carbonate, aren't we?
Yeah.
Okay. Anyway, but go on. Sorry, go on.
If it were hydroxide, the lattice energy would increase faster than the hydration. I mean, increase.
You mean increase more?
Yeah. So then hydroxide would be more soluble because the lattice energy increases more than hydration because of hydroxide's small size compared to the M2 plus. And then, so if carbonate would be larger than OH, so then the increase in lattice energy down the group would be less than the M2 plus because the carbonate ion is similar size to the cation. So lattice energy decreases more, which means that enthalpy change of solubility becomes more positive than the group, so less soluble than the group.
Okay, so that's all like a very strange anion because it's not a single atom kind of anion. These are polyatomic ions, and it make it harder for you to comprehend the actual size, right? Okay, let me give you some simpler examples, perhaps some metal halides. Group 1 metal halides. Are you ready? Okay, group 1 metal halides are a lot easier than group 2 carbonate or group 2 hydroxide because in group 2 hydroxide you have 2 hydroxide, here carbonate you have CO3 2 minus, complicated, right? Let's just talk about something simple. Let's just talk about group 1 halide. So you have lithium fluoride.
Okay.
You have cesium iodide. You have lithium iodide. And you have cesium fluoride.
Yeah.
Okay?
Yep.
So the thing back here is that lithium fluoride and cesium iodide very low solubility in water, so very insoluble in water. Lithium fluoride and cesium iodide low solubility in water, but the last two, lithium iodide and cesium fluoride, very very soluble in water, very high solubility in water. You get it? The first two, lithium fluoride and cesium iodide, very insoluble in water. Lithium iodide and cesium fluoride, very soluble in water. So you learn the general rule that all group 1 salts are soluble in water. But between soluble in water and very soluble in water, there's difference in solubility. So here are some examples here. Like I just give you two contrasting thing here, right? So the idea here is, can you explain why? Okay, and to help you explain why, I'll give you a relationship. So enthalpy of hydration, you can think of it as inversely proportional to the radius of the ion.
Okay.
You know the idea of inversely proportional? So you can treat the relationship like enthalpy of hydration is inversely proportional to the radius of the ion. Whether it's cation or anion, doesn't matter. because you hydrate cation is still exothermic. You hydrate anion is still exothermic because water has the delta plus and delta minus, so it's still going to be a favorable ion dipole formation, right? That's why it's exothermic, regardless of cation or anion. Okay, uh, and then the enthalpy of lattice, you can think of the relationship as inversely proportional to inversely proportional to the sum of cation and anion.
Yeah.
So it's 1 over R plus R minus. So it's the sum of the cation and anion. So lattice enthalpy can be treated as inversely proportional to the sum of cationic radius and anionic radius. Okay, there's actually the relationship actually has some stuff on like number of ions, and the actual formula is number of ions and the charge on the ions, but it doesn't matter. We know it's favorable because you have a plus and a minus in the ionic group 1 metal halides here, and I know that all of these, their number of ions will be the same because they all are of the general formula mx group 1 halides. So I wouldn't care about those things which are taken into a constant already. So the relationship is just 1 radius of cation plus radius of anion. So first of all, yeah, do whatever you want, but explain the statement. Why the first two has very low solubility in water, but the last two very soluble in water. You can take your time and think about it.
Enthalpy change of solubility is equal to the enthalpy change of hydration minus enthalpy change of lattice energy.
I would say it's always easier if you if you write an equation showing the enthalpy of solution for a group 1 halide, such as Mx, and then link it to the lattice from there. So that way, it's straight away you can see the relationship instead of having to remember the relationship.
Yeah, okay.
So just like the equation just now with the covenant, but you can start from, I don't know, general Mx, group 1 halide, right?
So mx gives m plus aqueous plus x minus aqueous. And then mx solid can be formed from the gaseous ions. And the m plus aqueous and x minus aqueous can be formed from the gaseous ions also. Okay. So
Yep, that's fine.
So lithium and fluorine are quite small.
Lithium fluoride.
Yeah, lithium and fluoride compared to lithium cesium or iodine. So both Li and F minus is small. So lattice energy would be the inversely proportional to the sum of the two radiuses. But then enthalpy change of hydration is just inversely proportional of one of the radius. But then we add it with there is the hydration for the cation and the anion. So both the radiuses are small, so that means the lattice energy the sum of the two radiuses will still be small. So that means 1 over r plus and r minus will be large, but then the enthalpy change of hydration for the m plus would be larger than that.
Okay.
So,
any further thoughts?
The combination of the enthalpy change of hydration for m plus and m and x minus should be larger than the lattice energy.
Sure. Okay, so when you say large, okay, large is a bad term to use when we are talking about enthalpy change. One thing you need to keep an eye out for is that what you learn at level is lattice energy is the lattice energy of formation, so that's why it's always exo. But lattice energy can also be lattice enthalpy of dissociation, which is breaking up the ionic lattice, which means it will be endothermic. So the error matters, and when you draw your diagram, you draw as lattice energy of formation. So when you say it's large can be, is it positive or is it negative? So when you're talking about enthalpy, it's always best to keep an eye out for exo or endo. And then when you think of the value, you also need to think of your cycle as well. And the equation, it has a plus or a minus in front. So a minus exo would mean it become more positive. Direction is important in enthalpy change, not just large. Large has no meaning, okay? It can be size, it can be value. It doesn't mean anything unless you know how to explain it properly, okay? You get the right idea. You already see the trend that is a small ion and small ion, a large ion and a large ions, okay? Not just large, small, small ion, large ion, not so soluble in water. Whereas it's the one small, large, and large, small. So basically small cation, large anion, which is lithium iodide, or you have large cation, small anion, which is cesium fluoride, very soluble in water. Okay. So do you wanna start explaining it? Like, so you know from your explanation on on the solubility of group 2 carbonate, you know it's the balance between the hydration and the lattice, right?
Yeah.
If one it's stronger than the other, basically the numerical value is higher than the other, then it will render the enthalpy of solution being more positive or more endo. So we are not comparing down the group. We are comparing absolute value here. Whereas just now it was down the group, so you can think of it being increasing straight away. But here, the balance is very important, right? And
Yeah.
you don't deal with this representation of lattice enthalpy being inversely proportional to the sum of the ionic radius in A level, but it can be a relationship that people just throw at you, and that's how you're asked to make sense of things. Yeah, okay. Let me just walk you through it. So when you have, so this is what I have. Can you see that? I mean, that is essentially what you will get, right? So the sign there is important. I've maintained the sign. So the sign of the enthalpy of hydration, I know it's negative, but based on the cycle, it's a plus hydration and plus hydration. So the first thing I keep in mind is that I have a negative 1 over the thing, right? Because it's a negative, and I know it's a lattice energy of formation. I know it's exo. So negative exo would mean it would be a positive term. Does that make sense?
Yeah.
So this is what I meant by like you must keep a close eye. You must be very clear on what is the overall sign going to be. Yeah, and then the hydration term is going to be the exothermic because plus hydration, both of them are exothermic. Okay, and actually I shouldn't use a one on top. Essentially, what I should do is I should have a constant over something because it was an inversely proportional thing. So what I could do is I could just put a constant like A, B, and C. It doesn't matter at this moment. Yeah, okay. Suppose the constant is just constant, and what is very important is the radius of the ions. They are the main variables here. Okay, cool.
Yeah.
So when you have small and small cation, small anion, so you know the radius of cation anion is going to be small. When you have large cation, large anion, the R plus plus R minus is going to be large.
Yeah.
Okay, and it so happened that when you have small cation and small anion, then the sum of the radii is going to be small, and that is when your lattice enthalpy is 1 over the sum of the ionic radius. So the smaller the ionic radius, the sum of the ionic radius, the bigger is the value of the lattice enthalpy. Means it's more exothermic. All right.
Yep.
Minus exothermic, minus something more exothermic means there is going to be a more positive term. In fact, because you are summing the radius of the cation anion, there is the more positive term. And then you can think of the enthalpy of hydration. It's small and small, so it's going to be exothermic and very exothermic and very exothermic. So it's still going to be negative. But I know to rationalize this observation is that the small and small, they are very, what was it? The small and small, very insoluble, right?
Yeah.
So that means the enthalpy of solution is going to be a very endothermic value. That's why it's low solubility. So the only way it can be more endothermic is when which term is a bigger value than which term?
Lattice enthalpy.
When the lattice enthalpy dominates over the hydration enthalpy, right, for small and small. Does that make sense?
Yep.
That's the only way you can get a very big positive and then plus the enthalpy of hydration, which is negative, is going to be less important here. That's how you can get the enthalpy of solution to be unfavorable in terms of dissolving small cation, small anion, right? On the other hand, when you have large and large, so the large plus large cation radius plus large anionic radius is going to give you a less exothermic lattice enthalpy. So it's still going to be exothermic, but it's going to be less exothermic, okay?
Yep.
But then the hydration, on the other hand, is also going to be less exothermic because 1 over bigger radius of cation, 1 over bigger radius of anion is still going to be exothermic. So again, it's a balance of these two. So which one is going to win? So it turns out that suppose when you have large cation and large anion, again, 1 over the, I don't know, which term do you think is going to be more important?
The lattice enthalpy.
It still has to be the lattice enthalpy, right? But I have a feeling it's the other way around. No, it's the other way around. But it's the other way around and the other way around again. So it's like the enthalpy of hydration term is more important, but at the same time, it's not saying that it's not soluble. It's just saying it's low solubility. So actually, the enthalpy of hydration, how do I say this? It's this is inorganic chem. There's a lot of trends. So instead of working with absolute values, you have to be playing around with trends and thinking of it in that sense. If I'm not mistaken, so 1 over big plus 1 over big. If the hydration dominates, then you will have negative,
Yeah.
but it's not very negative, and it's being offset by the lattice enthalpy, but not as much. Yeah, that's sorry. Let me just refresh this a bit clear. Sorry, I was just digging out this old problem. I haven't actually thought about this since I left uni actually, because yeah, we don't actually talk about this in A level a lot. But I'm pretty sure it's the enthalpy of hydration that dominates over the lattice. But it's just that the effect is very small. The effect is much small because when you have 1 over big plus 1 over big, it's always going to dominate against 1 over big plus big, because the big plus big is going to be huge. 1 over huge is going to be very small and inconsequential. So it's just the delta H solution here is approaching in the other direction. So I'm not sure if you get me, but it's kind of counterproductive to what we say in the first case when it's small and small. So this hydration for this one, the hydration is the more important term, but it's approaching it in the other direction, but in a way it's still contributing to the low solubility. Okay, the best compromise, you have the small plus large and large plus small. And because when you have small plus large or large plus small, the sum of the ionic radius hovers in between. So it's quite good there. Again, when you have small plus large plus small, enthalpy is the sum of the hydration of cation and hydration of anion. Only one of them is going to matter when you have small plus large and large plus small. Okay, but because you have one small one, the large one is inconsequential for the hydration. So 1 over size, whether it's anion, is going to be very, very exothermic. Yeah, very, very exothermic because very small. The 1 over large, not so important. But again, you have small plus large. Small plus large, 1 over small plus large is still not going to be as big as 1 over small. So the 1 over small, which is the hydration enthalpy, is going to dominate. It's going to be exothermic, and it's going to be very much more exothermic compared with the lattice enthalpy. So yes, the lattice enthalpy is still more exothermic than 1 over large plus large because it's large plus small. But again, because you have one very small ionic size, whether it's cation or anion, the one of the hydration, whichever one is smaller, is going to dominate, like really, really dominate over the 1 over the sum of the ionic radius. And because of that, you're going to get the enthalpy solution to be swerving towards the negative side, which means it's going to be soluble, much more soluble compared to the small, small and large, large. Phew, we spent ages talking about trends. Do you like inorganic chem? It's one of the driest topic of all, yeah, but it's something quite important as well. So what you do in A level is a lot of just useless trends and stuff, but like a lot of it can be rationalized using physical chem, using this. I haven't talked about it a lot, but if you know the real equation, then you have real variables, and then you can work out you can differentiate them, as in like calculus kind of differentiation, like differentiate enthalpy change with respect to the radius of the cation or radius of usually it's a cation because you're changing like group 1 size or group 2 cationic size. Then you can see how the enthalpy will change depending on the radius of the cations, and you can put in all the constant value and the computer can do the work for you, and then you can get the trend. Is it becoming more soluble or is it predicted to be less soluble, etc., etc. Okay, cool. I've only prepared have you learned about, so let's talk about physics, yeah, and also mechanics. Do you do mechanics or do you do statistics module, or you do M1 S1 in maths?
Statistics module only, S1 S2.
But you take physics, right?
Yeah, mechanics is okay.
Okay, cool. So you know about physics. How good are you with mechanics?
I'd say okay, yeah.
Okay, cool. Projectiles. Have you done projectiles in physics?
Yeah, we did projectiles already.
Okay, cool. Have you done spring theory, Hooke's
Spring.
law?
Yeah.
Okay. We're gonna be talking about particle on a spring. It's the basis of infrared. In infrared you have bond stretching and bond vibrating, right? You know
Yeah.
infrared.
Yeah.
Okay. So infrared theory of infrared can be modeled based on this Hooke's law. If you can imagine them as vibrating off each other like that, so you can imagine as particle on a spring. But instead of the two vibrating from both sides, what we're gonna do is we're gonna fix one side so that one side is not moving, one side is stationary, and it's vibrating like that.
Yeah.
This is the classic modeling of a particle on a spring. Okay, cool.
Yep.
So suppose if I have two bonds, such as a carbon-carbon bond, a carbon, what is next after carbon? Carbon-nitrogen bond, carbon-oxygen bond. Okay, so single bond, carbon-carbon single bond, carbon-nitrogen single bond, carbon-oxygen single bond. Okay,
Yeah.
how would their stretching frequency be affected by whether it's carbon, nitrogen, or oxygen on the other side? Are you able to model this? Let's start from Hooke's law. What does Hooke's law say?
That the force is proportional to the extension of the spring.
Okay, so it's a constant. It's what you call the spring constant, I suppose. And then it's F equal to K X, is it? Like how far you move, right? How far you move. Okay, cool.
Yeah.
And then this is the part where I can't explain very well. What does Newton's second law say? When you have a motion in one direction, yeah, what does it say?
Then there's a force which opposes that motion.
No, that is Newton's third law.
Oh,
Is it? No, Newton's third law say.
for every for every force there's an equal and opposite reaction.
Yeah, what does Newton's second law say?
Says that the force exerted is directly proportional to the rate of change of its momentum.
Okay, cool. So there's F equal to ma, or you can express it in terms of momentum, which is all right. Um, uh, this is the weirdest part of all. I can't really explain this well, but there's a link between this particle on a spring and this Newton's second law there. And I'm supposed to bring in something here, which is circular motion. What is circular motion in physics? Have you learned circular motion?
Yeah,
Okay.
centripetal force.
Yeah, what's the centripetal force formula? Like, yeah, how is it affected by the radius in which you move in the circular motion?
It's depends actually. Uh, there's two formulas we can. One is
Uh-huh.
mv square over r, and then there's also m omega square r,
What is omega?
the angular frequency.
Okay, what does angular frequency means to you?
The angle, the amount of angle turned in 1 second.
What's the unit for angular frequency?
It's just per second.
No, per second will be frequency. What's the unit for angular frequency?
Radians per second, or
Yeah, it's how far you move in that angle, right? Okay. And then the one is the angular velocity and one is a angular. What is omega again?
angular frequency.
Okay, angular frequency. So it says how you relate the angular frequency and the angular velocity. Then what you call angular velocity? When you have that mv square over r, what does v represent?
What is it's just the arc that is formed.
The what?
Uh,
So if there's that formula, F equal to mv square over I equal to m omega square R, label V. What is V? What is meant by V?
The angle turn swept by the radius, which is just the arc length.
What's the unit of the V then? Yeah, what's the unit of the V there?
Should be meters per second, and I
Okay.
radians.
Is this AS physics or is this A2 physics?
It's A2 physics.
Oh, is it? Okay. So is it radian or is it meter?
Angular velocity is omega r.
Angular velocity equal to omega r. Okay. So that is angular velocity because it is a velocity, so it should be meter per second. And when you relate it to radian per second, when you relate it to the angular frequency, okay, cool. Anyway, so yeah, the unit for v there is still meter per second. It's angular velocity. Okay, here's the weirdest part. I don't know how to say this, but you can relate the force constant. So instead of imagining it rotating in a circular motion, so what it actually does is you can have F equal to ma equal to m omega square x instead of r equal to kx. All right.
Okay, so yeah, all right.
So relating the angular velocity and the spring law, no, Hooke's law. Can you now get the relationship for the force constant? What is the force constant equal to? I mean, you will know it as a spring constant, but I will learn it. I will tell you that it's a force constant. Talking about how strong is this? How strong is the bond between the two atoms now that we are modeling? So what is K equal to? So F equal to ma, and you can model it as m omega square x, and that's equal to the Hooke's law.
There's G. F is equal to kx. F is equal to m omega square x. F is equal to ma, which means that K is f over x. So if we substitute force as m omega square x, then we get m omega square.
Okay, so K equal to m omega square. Can you then get me the frequency? Can you then make the angular frequency the subject? So make omega the subject.
Make omega the subject. So k over m, and then the square root of all of that.
Okay. What's the relationship between angular frequency and frequency? So frequency of oscillation and angular frequency, what's the relationship?
2 pi f. Angular frequency is equal to 2 pi f.
Okay, so f is just the frequency, and 2 pi because there's how much radius is covered in 1 second. There's angular frequency, right? Okay, can you express f as a subject then?
F is omega divided by 2 pi.
Okay.
So
and
frequency is square root of 4 pi square over, wait, K over 4 pi square
You got it?
Yeah, frequency is square root of K over 4 pi square m.
Huh? Can you show me how in the world you get 4 pi square? Can you show me your formula? Show me your working. Okay, that is all right. K is equal to, yeah, that is where you have messed up. So I agree with you that omega equal to K over M, and I agree with you that, did you get F just now? F equal to 1 over, or you shouldn't have moved the 4 pi square into there. You should have just left the 4 pi square outside. So F equal to 1 over 2 pi square root of K over M.
Yeah.
Okay. All right. That's actually the better form of it. Okay. This is I'm not sure if you have derived this before, but this is a frequency of oscillation as for a particle on a spring actually. Okay. There's actually a modeling again, because M is a stationary. So M is the mass that's moving, but you know that in an IR stretch that you actually have both of them moving. And this is just a model where you assume one is stationary and the other is moving. So you have to think about the relative mass that is moving. So when both of the atoms are moving, you come up with this thing called the relative mass, where if one thing is moving, then this mass that is moving is not actually just its own mass. It's related to the, it's called relative mass because it's related to the mass that you assume to be stationary when you are modeling it.
Okay.
When atom that's vibrating, it's not one end stationary and the other moving. It's both ends vibrating, stretching, right? That's why you have a stretching frequency. So that frequency you got there is what you call a stretching frequency. Well, it can be a vibrating frequency, but vibrating frequency is not modeled by this. Sorry, vibrating frequency. Oh, what's happening to me? Stretching or bending. Bending is not covered by this because bending is a different thing again. So if you have stretching and if you have bending, just moving things like water can go can get closer, slightly bigger, slightly closer, slightly bigger. Okay, stretching involves a slight change in the bond length, and it involves overcoming the force constant here. I call it the force constant because that's actually what you call a indication of the strength of the bond as well. So you can make K the subject. So if you make K, can you make K the subject as well? If you make K the subject, so K is equal to
mf square.
M omega squared. I can't even think straight today. 2 pi f squared. Can you give me the relationship of K and the stretch and the frequency?
4 pi square mf square.
Yeah. So K is really proportional to F squared. So what does this tell you? So K is an indication of how strong the bond is.
Okay.
It's called the indicative of the bond strength. F is the stretching frequency. If you see on the IR, you see on the IR value is in wave number. So wave number is Cm minus 1. It's a very stupid scale, but we have kept it for 100 of years because to change it now would mean that a lot of things will have to change, and people are used to IR being in wave number. Wave number is in Cm minus 1. It's not a standard unit. It's not a well-known unit, but it's a stretching frequency. It's a value of energy as well. It's a value of energy. So the higher the wave number, the higher is the energy required to bring about that change. So you will see that stretching frequencies are at a higher wave number than bending frequency because it takes lesser energy to bend than to stretch. Okay, so if you have a CC single bond, a CN single bond, and a CO single bond, how would you expect their if you rank them in terms of their stretching frequency, how would they rank? We have a CO single bond, CN single bond, and a CC single bond.
We assume that the carbon is stationary, and we're comparing the carbon, nitrogen, and oxygen. So oxygen would be heavier.
So?
So K is directly proportional to the mass and the square of the frequency. If the mass increases, then the spring constant increases. So that means more energy, more stronger. The bond is more stronger.
Okay.
So
it's quite a conundrum, isn't it? How would I be able to make this easier? Sorry, I forgot about that problem. It's such a shit problem. You can read about it on infrared. I'm sorry, I should have asked that problem. It's quite a shit problem to ask.
okay.
Yeah, I know your dilemma. I only realize it now. Like K is a constant, and if K is indicative, K is actually a constant. But if it's indicative of the bond strength, then you're gonna get conflicting answers here. In the interview, they'll try and guide you, so not to worry about that too much. Okay.
Sure.
I have one question actually. Have you? Yeah, that's it for today. Sorry, I have been very unprepared with it, but I've tried to cover as much as I can with you already. But the main point was the inorganic chem, like the trends and stuff, and you seem to have no problem explaining it. It's a lot of waffling through, but what's important is if you are asked about it in an interview, you need to be ready to draw some diagrams, some cycles, and to explain it from there. They'll make your life a lot easier to explain. Okay. My last question for you is, who won the Nobel Prize for this year? Or rather, do you know what was it won? What was it awarded to this year?
This year, not really sure.
Okay, it's awarded for something very important. It's for the discovery of for the invention of the lithium-ion battery.
Oh,
Do you know where you use lithium-ion battery?
isn't that the phone?
Yeah, there's the phone battery. There's your iPad battery. If you have a portable electronic device, it has a lithium ion battery that can be recharged. So it's not just lithium ion inside, it's got a lithium ion and it's got cobalt 3, cobalt 4 redox chemistry that allows it, to be charge, discharge, recharge, discharge. Recharge, you top up with power, it goes to one oxidation state, and then as you take off the power source, it uses the power source and dissipates it. So it shifts from one oxidation state to the other. So redox reaction can be favorable or unfavorable, right? And in a redox reaction, you can generate potential and you can generate energy, and that's how the energy is gotten out. But yeah, that's just the Nobel Prize for this year. One of the guy, John Goodenough, he was at Oxford and he was inorganic tutors supervisor then. So he's a solid state chemistry. I haven't touched a lot of solid state with you, but I mean it's a standard thing that you should read up on these things. Yeah. Okay. Tell me about chemistry Nobel Prize winners that you know.
Chemistry. Richard.
No.
Robert Wood. Robert Woodward.
Who is Woodward? What is he famous for?
Synthesis for natural compounds. He's the first one to.
Okay, so he's a synthetic organic chemist. Woodward. How many Nobel Prize did he win?
How many? I'm not sure.
He won more than one. One was for his there's something called the Woodward-Hoffmann rule. So it's quite a general rule that was done through computational study. But back then in 1950, 1960s, the computer weren't great. So he actually predicted it from doing like manual work. And the rule has been very consistently applied in predicting whether certain organic reactions will happen. So it's a physical organic chem. So it's not just organic chemist. He also delved into physical organic chemistry as well. Richard Feynman, I think you were gonna say Richard Feynman, unless you're gonna say the Richard. Was it Richard Feynman you were thinking of?
Yeah.
Richard Feynman is a physicist, yeah. Okay, so he's not a chemist. But yeah. Do you know any other chemistry Nobel Prize winners?
J.J. Thomson for the discovery of electrons.
Okay.
That's
Anyone else you know?
particle, I mean.
Who?
Wait, no, I don't know.
You don't know. You should read up on a few of those because it's unlikely personal question will come up, but you know like you know about the historical significance of like discovery of particles by J.J. Thomson, like who discovered the nucleus, who discovered how did they get the protons. So they did the gold leaf experiment. I'm not sure if you heard of it.
Gold leaf.
Yeah, they fired Sir Rutherford. He was at University of Cambridge before, Ernest Rutherford. So Ernest Rutherford and I think who was it you said discovered the electrons? J.J. Thomson. I think J.J. Thomson was Ernest Rutherford's student. So it's one generation leading to another generation. So it was they were both in Cambridge. Electrons were discovered by J.J. Thomson. So they knew then when electron was discovered, they knew that neutrons were present as well, but they couldn't detect neutrons until much later. So the neutrons are discovered the last. So it's the last particle to be discovered. So I think it was protons and then electrons and then nucleus. Sorry, not nucleus, neutrons. Do you know why? Can you suggest why? Why does it take so long to detect neutrons?
They're uncharged. So
Yep. So it's quite hard to confirm its existence until. So they know it's present. So they know about the chemistry and things, but like to prove its existence. Okay. We talk a little bit about X-ray crystal structures, right? So yeah, have you heard of diffraction?
Diffraction.
Not just X-ray diffraction, just diffraction in general. Have you heard of Bragg's law in physics? Single slit diffraction, double slit diffraction.
Oh yeah.
Yeah. And lambda equal to d sine theta. That is something quite important, you know, those constructive interference and stuff. So the Bragg's law was by it was formulated, not discovered, it was formulated by a father-son duo. I think the son is still the youngest Nobel Prize winner at like 25 or 26 years old because he won it together with the father. I think he's still the youngest Nobel Prize winner I'm pretty sure it was in chemistry, could be in physics, but double check.
Okay.
It's like what if something they asked, who do you think is the most worthy Nobel in chemistry ever and why? There have been so many important discoveries in chemistry, right? But like without knowing the inventor, let's say, so what would you say is the most noteworthy, as in the most important chemistry discovery of all time, in your opinion? Basically, let's just start with three first. Let's just start with three, then we can narrow it down to one. In your opinion, what do you think are the most important discoveries in chemistry for you? Top three.
Top three.
You don't need to know about its actual chemistry, but just what it is that's important to you.
I think second law of thermodynamics is there. And then
Oh, second law of thermodynamics. What's the second law of thermodynamics?
the entropy of the universe will always increase.
Do you know there was a Nobel Prize awarded for that? Do you know who got that Nobel Prize?
Not really.
He's the first Nobel Prize winner in chemistry. His name is. Oh no, that one is Boltzmann, isn't it? Look at someone named Van Hoff. Van Hoff is the first guy who won Nobel Prize in chemistry. He's a father of thermodynamics. VNTHOFF. You don't need to know a lot about his chemistry, but it's general stuff. But the one who came out with entropy a lot, he's got KLNW equal to entropy on his gravestone. Do you know who that guy is?
Yeah.
Boltzmann. He's the guy, part of the discoverer of the Maxwell-Boltzmann gas law. They're not the same person, yeah. One is Maxwell, one is Boltzmann. So that is Boltzmann, the second law of thermodynamics. That's your one of the top three. What are your other two?
Let me think. Let's see.
It's hard to choose, or you don't know?
I mean, there's not much I know, but
what I'm saying is that you don't need to know who won what and what was it for, but like in your opinion, like what are the three most important things that chemistry has contributed to you, in your opinion? So you say one is the second law of thermodynamics, partly because they govern a lot of stuff that happens, like why things happen, why some reactions don't happen. It's all governed by thermodynamics, right? Okay. Anything else that?
For organic, I guess. Let's see. I think the what's that? The spin for NMR.
Yeah. There's a winner for NMR. As a matter of look up the history of NMR. I'm pretty sure there's a Nobel Prize winner for NMR. If I'm not mistaken, it was 2 years ago. If I'm not mistaken, it was 2 years ago. And NMR has been immensely useful, really, really useful. Like today, I ran like 15 NMR, 15 NMR, like just proton NMR, and we won't talk about NMR now. But NMR is one of the most important discoveries in chemistry. But you know why infrared was very important? Because back then they don't have NMR. Back then they only have infrared. So they use infrared to identify their stuff all the time. And it's quite amazing that people like Woodward, he even before X-ray, even before NMR, he could pinpoint the correct structure just by using all the data, mass spec, infrared.
Yeah.
There was before more advanced technology like we have these days. So really, really clever guy, really, really capable organic chemist back then. There's your 2 out of 3 already. What is your third one then? I mean, it's just your personal opinion. There's no right or wrong. It's just
Yeah.
like
Third one. Let's see. I want to say electrolysis.
sorry.
Electrolysis for batteries. In battery.
For battery. Okay. You don't do electrolysis in battery. What you have in battery is not electrolysis. Electrolysis is breaking them up, whereas in battery you are generating potential. So That's something you need to keep an eye out for in A level as well. What is a cell, and what is a electrolysis is breaking up. It's not generating. It's not generating potential. What you want is something to generate potential. That is a battery, and that's the best. Yeah. So that's the difference. I'm pretty sure no one has won anything for electrolysis, but hey, someone won something for lithium ion battery this year. So yeah, I mean like you don't need to know who won what year, but these are interesting historical facts, and you should have a few chemistry heroes to you as well, like based on their discovery, for example. One guy, Linus Pauling. I'm not sure if you heard of him. Pauling.
No.
Linus Pauling, Pauling, 3 Nobel Prize.
3.
In chemistry, 1 in Nobel Peace Prize. He publishes everything. He does biology, he does physics, but he does mostly chemistry. But he very clever guy. He's the guy who came up with Pauling electronegativity scale. And he's also the guy who came up with, I forgot something else already. So that's his other Nobel Prize. Einstein won the Nobel Prize in physics, but it relates to chemistry as well, the photoelectric effect, right? So there's a bit of quantum chemistry. Erwin Schrödinger, there's the cat in a box, the particle in a box, the cat problem, is it dead or alive? Yeah. He is a physical chemist. I think he got it for physics instead of chemistry. So the different branches of chemistry, there's biochemistry, there's biochemistry, there's chemical biology. Similar but not exactly the same. There's physical chemistry, but there's also physics. They kind of overlap, but they're not exactly the same. A lot of how about famous chemists from Oxford who have won Nobel Prizes. One of them is a female. Her name is Dorothy Hodgkin. I'm not sure if you heard of her. She got the crystal structure of insulin. So if you know people who are diabetic, now they have synthetic insulin, and we know how to make it as an organic chemist because we know the structure. And how we know the structure is because we got a crystal structure of it. And Dorothy Hodgkin is a crystallographer, so she got a Nobel Prize for the crystal structure of insulin. And because you know how it looks like, you can make it. And if you can make it, you don't need to get it from animals. Because I'm not sure if you know the history of insulin, they used to get it from animals. Yeah. You can ask your brother, history of insulin. So they get it from animals then, but it's the same thing with synthetic drugs. So let's say there was a flu, a very serious, I think it was something a few years ago. There's only one kind of drug that they found was effective in their testing. And it was from a natural source. And because you need to give it to a lot of people, you don't have enough from natural resources. It takes time to get it from natural resources. So people have been trying to get structure, and then you can make it in the lab. Yeah. Very challenging. Organic synthesis is very challenging in the lab because if you have a molecule with 20 chiral center, 20, yeah? Yeah. Do you know how many possible isomers are there?
2,000. Wait, no.
Okay, if you have a molecule with 2 chirals, 2 to the power 20, do you know that only one of them is the one that is effective? And if you start from 0, if you start from the most basic thing, you have to control every one of the way, and then it's just crazy. Natural synthesis, sometimes they win Nobel Prize, but not every year. Like usually they kind of alternate between the different areas. I'll leave it for talk today. I think I won't talk to you for like a month or so. In about a month time, around, you will have set your PAT, not your PAT, your TSA. When is it? Is it first? End of this month, not November?
No, 30th October.
Is it when?
I think it was the first day.
Okay, things have changed then because it used to be always the first Wednesday of November. Anyway, that's fine. Should be all right. I hope.
Yeah.
Practice a few papers. Make sure you do very well in it. Hopefully the interview invitation will come middle of November, and then for the actual Skype session, you need to arrange. You need to arrange it at some point so that you can go to a place with better internet connection.
Yeah.
So that it will be lagging, but they can wait. Okay, so there's no need to worry about that, and just do your best in your exams, and I'm sure everything will come out to be all right. Make sure have you paid for your UCAS yet?
No, I'll pay it later.
Just make sure that everything is settled because it takes some time to send it out before the 15th as well. So once you're satisfied with everything, just get it sorted out. Okay.
Yeah.
Any questions?
No, it's
Okay, I've asked enough today. Okay, I'm quite tired actually. I think
Oh.
you're tired as well. Let's call it a day. I will see you when your A level is over, and then we'll talk more. Okay. Is chemistry paper 4 your first written paper?
Yeah. Paper
Ready
4.
for it?
Yeah. Yep.
Yeah, you have no problem in there, I'm sure. But yeah, the usual thing, just don't contradict yourself. In terms of organic synthesis, usually A levels are pretty simple, but there's always like one or two challenging questions, and treat those challenging questions as your preparation for box bridge, and just explain them the way you can. Um, uh, don't feel afraid about using stuff you learn from these kind of interviews like resonance, inductive effect. So those are sensible things. You can even find them on Chem Guide. They're not wrong chemistry. They are even on Chem Guide, which is suitable for A level. It's just that they don't teach you a lot in A levels. And then if you know a lot, and if you think it can help your explanation, why not? If it doesn't, then don't bother. Okay. Good luck, and yeah, see you in a month time. Right? Read up
Okay.
read up the James Killer and Peter Waters book when you have time. And when is the last of your written paper?
Last about 8th of November, I'm pretty sure.
Oh, that is quite early. Yeah. Okay. Yeah, we'll talk in a month time then. Cool.
Yeah.
All right. Goodbye.
All right.
Good night.
Bye.
Bye.
Yeah.
Okay.